universal glitch, killing quantum computers. Internal roadmaps from the architects of quantum computing reveal a brutal engineering tax. For every single stable logical qubit, approximately 1,000 failure-prone physical qubits must be built and controlled. This staggering overhead confirms that the primary obstacle is not manufacturing scale, but a fundamental conflict with physics itself, a universal glitch called decoherence, where the slightest environmental interaction can irrevocably destroy a calculation. The operational paradigm of a quantum computer represents a fundamental departure from the deterministic logic of classical computation, deriving its immense potential from the counterintuitive principles of quantum mechanics. Through superposition, a single quantum bit, or qubit, can exist in a probabilistic combination of both 1 and 0 simultaneously, while entanglement allows the states of multiple qubits to become inextricably linked, regardless of the physical distance separating them. This capacity for parallel state representation is the source of its theoretical exponential speedup for specific classes of problems, a potential first articulated in the foundational work of physicists exploring computation at the atomic scale. Yet, this theoretical omnipotence is anchored to a physical reality of almost unimaginable delicacy. This stark disparity between computational capability and operational instability constitutes the fragility gap, a profound chasm, separating the elegant mathematics of quantum algorithms from the noisy, chaotic reality of their hardware implementation. A quantum state is a profoundly transient phenomenon, maintained in a delicate balance, that is instantly and irreversibly shattered by any form of environmental interaction, from a microscopic temperature fluctuation to a stray photon. This extreme vulnerability establishes the core paradox of the field and poses the central question driving the entire enterprise. Why is a machine conceived to solve the universe's most complex problems, so utterly defenseless against its most subtle disturbances? This is not a peripheral engineering challenge. It is a central thesis confirmed in peer-reviewed literature, such as papers found in journals like Nature Physics, and implicitly acknowledged in the strategic planning documents published by industry leaders like Google, Quantum AI, and the teams behind the IBM Quantum Roadmap. The immense computational power of a quantum system is derived directly from the very physical fragility that threatens its existence at every nanosecond. The central mechanism responsible for this catastrophic fragility is known as quantum decoherence, a process that constitutes as the most formidable barrier to fault-tolerant quantum computation. A quantum computation's power resides in the delicate, coherent superposition of its qubits. This coherence is not a static property, but a precise and dynamic phase relationship among quantum states. Decoherence is the irreversible decay of this relationship, occurring when the quantum system inevitably interacts and becomes entangled with its surrounding environment. This interaction effectively leaks the quantum information into the universe, causing the qubit's superposition to collapse into a definite, classical binary state of either 0 or 1. The environment in this context is not a distant abstraction, but an immediate and pervasive antagonist, encompassing thermal vibrations in the silicon substrate, stray electromagnetic fields from control wiring, and even ambient photons, to a qubit held in a state of carefully orchestrated superposition. An interaction with a single stray particle is not a minor perturbation. It is an act of measurement that annihilates the ongoing computation. This phenomenon is the practical manifestation of the observation paradox, where the very act of a system being observed, even unintentionally by its environment, forces it to abandon its quantum nature. This is analogous to attempting to balance a needle on its tip while a freight train passes a mile away. The slightest vibration from the outside world guarantees the collapse of the precarious state. Research published in journals like Nature Physics and conducted at institutions such as the Max Planck Institute consistently affirms that this is not an engineering imperfection to be eliminated, but a fundamental feature of physical law. The universe is constantly measuring, and in doing so, it enforces a classical reality upon quantum systems. This relentless assault establishes the decoherence wall, a temporal boundary measured in mere microseconds for many current systems, beyond which a coherent quantum state cannot be maintained. This is distinct from, though related to, the quantum Zeno effect, a counterintuitive principle, where frequent deliberate measurements can paradoxically freeze a quantum state and prevent its evolution, highlighting the complex role of observation in quantum dynamics. Decoherence is not a flaw in the machine's design, but is rather the intrinsic process by which the universe resolves quantum ambiguity. In direct response to the fundamental threat of decoherence, the field has converged on two principal engineering battlefronts, one of informational redundancy and another of thermodynamic isolation. The first strategy, quantum error correction, or QAC, it concedes the inherent unreliability of any single physical qubit, and instead encodes the information of one pristine, fault-tolerant logical qubit across a large distributed ensemble of them. This approach, detailed in theoretical frameworks published in journals like LI Quantum, functions by constantly polling the constituent physical qubits for errors and applying corrections without ever directly measuring, and thus collapsing the core logical state. This protective redundancy comes at an astronomical cost, creating what is now commonly referred to as the error correction tax, an overhead ratio where, according to roadmaps from leading labs, it may require 1,000 or more physical qubits to create a single, stable logical one. The second parallel strategy is to wage a direct war on environmental noise through extreme physical isolation, an effort that culminates in the cryogenic nightmare of maintaining the quantum processor at temperatures infinitesimally close to absolute zero. This is accomplished using complex dilution refrigerators, massive, multi-tiered apparatuses, often called the Chandelier, for their cascading gold-plated structures, which are designed to cool the processor to a few millikelvins, a temperature far colder than deep space. Yet, as analysis from institutions like MIT Research demonstrates, this creates a profound engineering paradox. The very control wires and microwave pulses required to operate the qubits generate heat, creating a thermal dissipation bottleneck where the control system actively undermines the cryogenic environment. This is akin to trying to keep a single ice cube frozen inside a blast furnace, where the apparatus of control becomes a primary source of the very noise it is meant to suppress. Engineering a quantum computer therefore requires simultaneously managing a brute force, informational defense, while fighting a losing thermodynamic battle against the system's own operational heat. The culmination of these immense physical and informational challenges fundamentally reframes the narrative of progress in quantum computing, revealing a critical scalability impasse. For years, the public-facing metric of success has been a simple tally of physical qubits, a figure that suggests a developmental trajectory analogous to the exponential growth of classical transistors described by Moore's law. This comparison, however, is profoundly misleading. The primary obstacle to a functional, larger-scale quantum computer is not a matter of manufacturing density, but of qualitative resilience. It is a battle against the fundamental forces of entropy and information loss, not a problem of miniaturization. A processor with thousands of low-quality qubits that decohere in microseconds is computationally inert, incapable of executing any algorithm of meaningful depth. As a result, the critical benchmarks for progress, as outlined in the strategic publications from research leaders like Google Quantum AI and within the IBM Quantum Roadmap, have shifted decisively from quantity to quality. The truly salient metrics are now coherence time, the duration for which a qubit can maintain its fragile quantum state, and gate fidelity, which measures the accuracy of the operations performed upon it. Improving these figures is an exponentially harder problem than simply fabricating more qubits, as each additional component introduces new potential pathways for noise and heat to infiltrate the system. The industry's strategic pivot acknowledges this reality, focusing intense research on reducing error rates in devices like the Sycamore processor, to cross the critical threshold where quantum error correction becomes viable. The ultimate objective is not merely to build a machine with a high physical qubit count, but to construct the first truly fault-tolerant logical qubits, the stable error-corrected computational units that will finally unlock the power to solve problems beyond the reach of any classical machine. The true bottleneck for quantum scalability lies not in the number of qubits built, but in their individual ability to survive the universe's relentless effort to observe and collapse them. The staggering 1,000 to 1 overhead required for a single stable qubit is the ultimate confirmation that quantum computing's greatest enemy is not a technological limit, but a fundamental law of physics. This universal glitch reframes the entire endeavor, shifting it from a race for sheer quantity to a profound battle to shield a fragile pocket of computation from a universe that is relentlessly trying to observe it. The core challenge is not just to build a more powerful calculator, but to architect a system capable of hiding from the very reality that grants it power. If this in-depth analysis of the physical barriers to quantum supremacy provided value, please consider supporting our work here at Tech Dissect Official. Given the immense challenges of both cryogenic isolation and the error correction tax, where do you predict the most critical breakthroughs will occur? In the material science, creating more resilient qubits, or in the theoretical design of more efficient algorithms to overcome noise? Thank you for joining this investigation. We'll see you in the next deep dive, where we'll analyze why the global transition to renewable energy is creating an electrical grid so complex and fragile that it may be physically impossible to control.